Yeah, I hope to see some of you again next semester too. It's we've only been able to cover, the solar system in this class for the most part, but a lot of the really, really fun mysteries are outside of our solar system. And so what I want to do today, and I'm not sure how long this is going to take. Maybe we'll finish early, maybe not. I'm not sure. But the point is I do need to finish up a couple of things. We didn't get to talk about comets last week, and I at least want to make sure you know what a comet is before I leave this class. But I want to review kind of I want to tie all this together, right? And I want to steer us towards the ideas that we're going to be dealing with next semester in case you're able to join us. I want to give you a preview of that. So we're going to be dealing more with the myth and cosmology, right? Because next semester, when we talk about what's happening outside of our solar system, we're really starting to talk about the universe as a whole, the physical universe. And so the cosmology comes into focus by the end of next semester, where we're really trying to paint a picture of what this place is and look at how all of our ancestors thought about this place too, because that's been a huge concern for almost all of time. And so we'll get even deeper into those questions next semester. And so I want to at least paint a little picture of that. So let's check out comets. Let's review some of the really cool, outstanding mysteries that we've talked about this semester. And then let's talk a little bit about where this could be headed. And I'll try to put a bow on the whole experience for you. But before I get to that, let's just go over a couple of things about comets, because they're really, really interesting. Good morning, guys. And I guess, before we do that, does anybody have any thoughts about meteors or anything like that? Any questions from the last lecture? Any noteworthy ideas, fears, concerns? You have a thought? Yeah?
Yeah. I was really intrigued by the asteroid mining.
Asteroid mining, yeah.
And the size of the actual meteor, I couldn't remember if it was 10 kilometers.
No, they're only like 20 meters across, I think, yeah.
Yeah. So
Very small, very, very dense.
just amazingly valuable.
Unbelievably valuable, yeah.
We just don't even know what's really there.
I mean, yeah, we really don't. But again, a lot of these estimates are done by looking at the density and trying to imagine. I assume they get some polarization measurements to give them the magnetic properties.
With the collar?
Yeah, with the way that light sort of scatters off of them.
Okay.
The way that they re-emit light, the way that they glow when they're heated, things like that. So, yeah, we don't know a lot. There have been some, I believe they've launched, I don't know where this is, and I don't know the name of the mission, but I believe that they're on their way to an asteroid right now to scrape some pieces off it. They may have already done that, and they're returning at this point. It's pretty cool stuff, and it's going to be a huge economy in the future for sure. But, just like any new market, you run into all the same political, well, I hate to say political to sort of dumb it down, but there's human rights at stake too, right? Because somebody's going to be stuck doing that work. And
We can do that. Are we going to be able to use them like we use a slingshot on a planet?
well, that's the other concern, is that somebody's going to turn them into weapons, right?
Right.
But yeah, the plan is to drag them back here and mine them in near-Earth orbit, as far as I can tell. But there's a lot of resistance to that. It's like, if we can't get along on Earth, do we really want to be starting fights in space over things? It's a really big open question. And I think where I ended last time was something like, I have no idea how this is going to work out. Yeah, it's hard to believe that we've... Anybody watch that Netflix show that I think it's called Chimp Empire or something like that? Chimp something. Did anybody see that? Oh, it's so good. They basically follow these chimps around at this big nature preserve, and just like one troop, one little band of chimps. And they basically they behave in some of the worst ways that humans behave, They essentially go on these warring rampages against the other tribes for really no good reason other than to, sort out their own hierarchies. A lot of the reason they go to war is to show who's the toughest person in their own tribe. and set up their own hierarchies. And it's so interesting that humans are still doing that after all of these years, right? We have spacecraft that can go and visit Jupiter, but we're still kind of can't figure out how to get along in some sense. Now, it is worth pointing out, though, that we've never seen less war on the planet than we have today, by a long shot. So it's been one of the most peaceful periods, particularly since World War II. World War II was really gnarly, of course, and World War I was perhaps even more gnarly. But since then, it's been one of the most peaceful times that the planet's ever seen. So there are still conflicts, and there's definitely threats and different cultures that are warring, even in our own country. But in terms of outright violence, we seem to have leveled it off significantly. And then, it's also poverty, right? So I think 200 years ago, something like 90% of the population was concerned with eating every day, right? Farming their little plot of land and just trying to survive through the winter. And now it's less than 10% today that are in that position. So things have gotten a lot better, but they almost need to get a lot more better before I think that we're safe mucking around in space, before we can trust ourselves with bringing asteroids back to our orbit and so forth. So in some sense, it's like, keep doing what you're doing, humans, but you're going to have to learn I think that oftentimes it's like, I don't know if you guys have, probably a lot of you have done athletics or art or music, or, it's one thing to get good, to get decent at a sport or at a musical instrument or something. You can get pretty good pretty fast. But the last little inch on that mile can take a lifetime, right? So perfecting your behavior at anything is really what separates out really the pros from everybody else. And so I think that we're kind of we're worming into that moment really as a whole species, where we have those final inches to go in terms of smoothing out the situation. We have the wealthiest nation that's ever existed by far that we live in right now. You look around and the roads are impeccable. The supermarkets are full of food. It's really a wonderful, wonderful thing. But there's really huge problems too. There's a lot of conflict between people. People are cut off from one another. There's homelessness issues, right? There's drug issues that are unresolved. There's the for-profit prison system. We have 5% of the world's population and 25% of the prisoners, and people are making money off that. It's like, there's a lot of things we could sort out to make this place a lot better. So anyways, I don't even know where I'm going with all that. Back to comets. So comets are really interesting. This is the main thing I wanted to share with you guys before we move on from this. Comets actually have two tails to them. This is pretty cool. And the interesting thing is that the tails always point away from the sun, right? They're not necessarily, and in particular, of these two tails, there's one that's kind of a rocky, dusty debris that's getting these particles are getting ripped off the comet by the solar wind. We'll deal with solar wind next semester, by the way. Really, really fascinating phenomenon. And then there's this gas stream, right? So vaporized, sublimated material that's in the gaseous phase. And that gaseous one is going to be, since it's lighter, it's not going to trail as much as the dusty part of the comet, right? So I think I'm not sure when our next really good comet's going to come around. There was one when I was a kid that was just amazing. There was one I saw up in Portland a couple years ago that you kind of had to squint or use binoculars to see it. But if you do get a chance to see one of these comets, it's just absolutely stunning. And you can see the two tails off of it too. So you can all tell your friends next time that comes around exactly how that works. Recently, we actually went out and flew out to one of these comets, which was pretty cool, and actually landed on the thing momentarily. This was 2014, the Rosetta mission. And one thing they found that was kind of cool was that as this thing got in its closest approach to the sun, that's when it started sublimating the gaseous molecules, right? Because remember, we talked about last time I mentioned the difference between comets and asteroids. These things are kind of like dirty snowballs, right? So they have some dirt and dust and stuff, but a lot of it is ice. And so the sublimating ice is what you're going to see in this vapor stuff. And so what happened was that just for a few minutes, this was a tiny little comet, right as it got close to the sun, its closest approach, which wasn't that close to the sun or anything, it started streaming, and they caught that. That's what you're seeing in this picture, is like the streamer actually turning on, right, like a spigot, which is really cool. And by the way, this thing is very bizarre looking. It has these two lobes. Nobody expected that to be the case. They don't really understand it, right? Nobody knows why it is the case. Now, about, I don't know, I don't want to say half, but a good portion of the comets that we see, they more or less reside most of the time out in this disk. They call it the scattered disk, which is part of those trans-Neptune objects that we talked about. There's a little reservoir of them beyond Neptune out here. You can see that's Jupiter, Saturn, Uranus, and Neptune. And these kind of hang out there for the most part, and periodically they get launched by whatever disturbances into the interior. Now there's also these really excuse me, there's these really long period comets that sometimes take millions of years to come around periodically. And these ones, in order to explain them, we actually thought up this idea that there was an even bigger scattered disk that was far, far away. So if you extend this ellipse all the way out to where it naturally would terminate at its farthest point, you reach this thing that they call the Oort cloud, right? And it's hard to even comprehend how far the Oort cloud is away, right? It's light years away. It's very, 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 very far. And this is essentially, I think I've started to think about it as almost like a foam that's in between solar systems, because the Oort cloud is basically at the edge where you basically have another solar system starting right after it. So there's almost this like foam of really God knows what. People don't know. There's speculations that it's even full of planet-sized bodies that we don't know about. It's possible. But for the most part, icy debris, junk from solar systems that's left over, it's all piling up there. And so that's kind of the final frontier of the Oort cloud. And of course, its existence was essentially deduced because where do these long period comets come from? They must be getting kicked out of some reservoir, just like these short period comets are getting kicked out of the scattered disk. So entirely hypothetical, these Oort clouds. We haven't really been there in any appreciable form. But it makes sense that there should be some pile of debris, some reservoir of material out there. So that is the absolute edge of what we know. And of course, it's, as we've talked about all of these things, you've probably gathered that we know less and less the further we get away. So we know the absolute least about the Oort cloud, and we know the absolute most about what's underneath our feet right now, right? So that's it. That's the solar system. And there's some incredible mysteries that we've encountered along the way, right? I think that, I mean, just to remind you as you guys walk away and you want to think about this, things to keep an eye on if you're interested in science and you check out the science headlines when you go through your news feeds or whatever. The cores and magnetism are a huge, huge mystery, right? The basic theory that I laid out to you with this dynamo system and these convection eddies that are swirling material that basically create these little solenoid systems, these electromagnets, that theory is troubled in some sense, right? Because it makes a lot of sense for Earth, where we have these nice convection, the possibility of convection, a lot of liquid core, right? The core and a lot of liquid magma, even all the way up to the surface in some sense. But what about places like Venus that have the same thing going on, but they don't have magnetic fields, right? It's very, very strange. So I don't even have a hypothesis for you on that one. I find it very, very strange, and I expect that our understanding of what's going on is going to, it's going to expand the more that, especially as we do reach out and start exploring Venus and understanding what's going on. We have a mission plan for the 2030s, I think. Probably learn a lot, but I think a huge part of it's going to be understanding magnetism itself, right? And I kind of breezed through this back at the beginning of the course when I tried to explain to you how magnets work. Now, how I explained it to you is in terms of atoms and the action of the actual material of the atoms, and I think that's a reasonable way to think about it. But that's generally not the way that people think about magnetism. They think about it in terms of equations, and they think about it in particularly in terms of how it relates to electricity, which is also understood primarily through mathematics. There's not a very good material understanding of magnetism itself, right? So I guess what I'm trying to say is that all these things fit together. The better we understand what atoms are doing to create magnetism, which is basically magic at this point. We have equations that say how the magic works, but we don't necessarily have a good material model for what the atoms are doing to one another. And so I tried to propose to you guys some way of thinking about that that's congruent with the mathematics, but it's a far from accepted way of doing it. So I think that the more we understand the fundamentals of physics, the fundamental material reality, the better we'll have a chance of understanding this mystery in particular, but many of the other ones as well. So that's something to keep an eye on. How magnets work, it's something you can ponder for a lifetime. Somebody's going to absolutely nail it at some point. And then why it is that some of the planets have magnetism and some don't. It's certainly going to be really important if we want to find another home, which is, of course, a huge project of our space exploration. We touched on the other project, which is to make money, right? So you get these asteroids, that's a huge economic boom. The whole world financially only really works as long as economies grow, which is an interesting sort of pitfall of the system that we live under right now. It's never okay with stasis, essentially. If your company isn't growing, your company's dying is one way to think about it, because it'll be outcompeted and sort of driven into extinction. And so people are always looking for new sources of resources, funny word, new things to extract, and so that's a huge part of this story as well. But part of it, getting back to magnetism, is finding a home. And it seems like the most amazing thing about Earth, there's a lot of amazing things about Earth, liquid water is essential and so forth, but we have this amazing magnetic field that nobody else has. And so if we can understand, maybe we can understand how to reanimate magnetic fields on other planets. Maybe we can come up with synthetic ways of generating that. I talked about it with Mars a little bit, setting up a sort of satellite that could generate an artificial magnetic field. But magnetism is at the heart of all of these projects. It's so important, and it's so poorly understood all the way down to the atom as far as I can tell. Remember, mathematics are fantastic, right? They're very good for engineering, but they're not necessarily going to give you an explanation for what's happening, right? So I think the story bears repeating that you could have, we could all be in a magic show right now, and I'm up here, and I'm performing some illusion, right, where I'm like sawing a woman in half. And it looks very much like I'm sawing a woman in half, and you can create a mathematical model of the room, and you can show exactly how precisely from every angle that I sawed the woman in half, but you still wouldn't realize that the woman was just lifting her legs up inside of the box and didn't actually get sawed in half, right? So that's the danger of just fixating on a purely empirical mathematical system of science, is that you run into these problems where the conclusions you come up with are sometimes extremely bizarre, if not even supernatural, right? And we're going to talk a lot more about that next semester, because we're going to be dealing with all these spooky sounding things like dark matter and black holes. And the case that I'm going to build for you is that those are actually just things we don't understand. They're not necessarily proof of superstitious bodies themselves, right? So, but we have a tendency to say, well, the math says this, and therefore it is so. And I would submit to you that, yes, the math could say that this woman's getting sawed in half as well when she actually isn't. It's just a matter of rationalizing what could possibly be happening where you can't see. And that's the trick, because all we have in astronomy is light. And so not only do we have to say what we see, but we have to rationalize, right? We have to use our imaginations to propose hypotheses for what could actually be happening. And that's the really tricky side of things, because in astronomy, you can't necessarily prove hypotheses, right? You can say which ones make more sense than others, but you can't travel, 100 light years, 100,000 light years outside of our galaxy and check out other places. You can only interpret the light and try to make sense of it. All right. We've also got this, I talked about the cores enough. It's also this mystery too, right? So I guess the central mystery in planetary science is the formation story, and that's kind of what this course has been dancing around over and over again, is how all of these planets formed. And the story that we've been left with is very much a story that, well, the story that went into, say, the creation of your textbook and so forth is one that has been around in its more or less current form for 300 years. It was proposed by the philosopher Immanuel Kant, right? Not even a scientist. And it was a good idea. And people tried to come up with better ideas, and they couldn't do it, and they couldn't do it, and they couldn't do it. But there's problems with that, and not the least of which is this, right? I mean, the planets, some of them are tilted on their sides. There's moons that are orbiting the wrong direction. Venus is spinning the wrong direction. Most of the angular momentum in the solar system is not in the heaviest object, in the sun. It's in Jupiter. That makes absolutely no sense according to like a basic disk that kind of condenses on itself, like the figure skater. You would expect the thing that's heavy at the center to have all the angular momentum. But that isn't the case. And so my sense is that and I think that we're on the edge of a very new understanding of our own solar system, which is a much more modeled and a story with a lot of, let's say, diversions and side stories. And, you know, we're having to start to think about things like, well, maybe the solar system over billions and billions of years isn't this stable, beautiful thing that the early planetary scientists, Newton, Kepler, Tycho, they imagined it, right? They imagined, wow, it's so perfect, all of these beautiful resonances, it's so stable. You know, God must have put it here just like this. And people have held on to that idea all the way up to the present, because I think that the alternative that things change dramatically and perhaps catastrophically periodically is a very tough pill to swallow. It's not something that we're very interested in. There's a little bit of a head in the sand paradigm playing out. So, you know, when I look at all of this diversity of these different planets and their shapes and their axes and their tilts and their orbits, which aren't perfect, I have to think that there's been some different events over the past that have led to these. And nobody can say what they are for sure, right? And a big part of that is, how does something that's been, you know, let's say moved from a new place or been kicked on its side by whatever mechanism, how does it get stabilized again so quickly? That's another problem that people haven't figured out. And I think that's a huge reason why the catastrophism isn't seriously investigated, as you know, people aren't willing to put those hypotheses on the table per se, because they don't understand how you can stabilize the orbits after something traumatic happens, right? So we can make models for how a passing star would destabilize orbits, but how do you get them back stable all of a sudden? People don't totally understand that right now. So, but things are definitely on the move with all of this. You know, I was gonna talk about Mars. Mars has got some incredible mysteries too that we didn't entirely talk about. This is an article that came out not too long ago. We used to think Mars, you know, it doesn't have a magnetic field, but we used to think, well, it's geologically dead. It doesn't have flowing magma, and so that makes sense, right? But recently, this team actually proposed that they did detect evidence of magma plumes on Mars from some of the from some of just the different readouts that they got in their orbiters and in their landers, and looking at seismic activity beneath it and so forth. And so there's this proposal, well, maybe Mars does have some flowing magma and so forth, but it still doesn't have a magnetic field. So what's going on? That doesn't, again, just like Venus, this is very bizarre. Mars also has very, very strange tectonic features, right? It's got this insane gash across the side of it. What's up with that thing, right? I think that the standard model for this gash is that it was sort of a cooling process and it ripped open as it cooled. But I don't know. I mean, what do you guys think? What does that look like to you? I don't know. It kind of looks like it got whacked by another planet to me. But I don't know. That's not a popular theory. So there's also the possibility of the liquid, right, on Mars, because half of Mars is very different than the other half of Mars. The North Pole is very flat, and it has almost looks like a floodplain compared to the South. And so there's this idea that maybe it had water in the past. Well, what happened to its water? Maybe whatever happened to its water followed from whatever happened to its magnetic field, right? Because once you don't have that shield up, we've seen in these other exoplanetary systems that the sun's very brutal on these planets, right? You can lose your atmosphere very, very quickly. I think I mentioned to you that last week that Pluto's lost something like 20% of its atmosphere in the last few years, right? These things don't stick around very long after things are destabilized. Yeah.
That crack or that line on
Yeah, the Valles Marineris.
Yeah, it looks, I mean, I like to make things up, but it looks like it drags against something with its rotation.
I know.
more than it
I
hits.
know.
And, cracks usually aren't straight. Even, no matter what, when they cool, when they whatever, they don't really form like that. They form jagged like lightning.
Yeah.
It's in my opinion.
I know. I have trouble with this, and that's why I wanted to throw it up there, because I just want to point out some mysteries, These are questions that I expect people will have better answers for in the future than they do today. I had this experience since I was a very little kid, and I encourage you guys to have the same experience. I would often hear stories in science class or whatever. I would go to the library when I was a little kid and read these science books. So I was like a little bit of a nerd. And some of the explanations just didn't make sense to me. And a lot of those explanations are turning on their head right now. And so I think you guys got to trust that intuition. That's what I really want you guys to come away from this class. None of you guys are probably going to become scientists. That's fine. But that doesn't mean that you're not smart and that you're not capable of looking at something that doesn't make sense and actually thinking, well, I don't know about that. And I think that's really healthy because that encourages the scientists to actually rethink things when enough people are raising their hands and saying, I don't know about that. Like the comet one was a huge one. I was told when I was a kid that all the water on Earth came from comets, right? And I went to the ocean for the first time and I was like, I don't think so, right? I was like 10 years old. And so that's one that's basically receded into the mist now. That's not the way that people, for the most part, think that the water came to Earth. In fact, most of the water on Earth is below our feet, right? So there's all of these little things, and I think when you see stuff that doesn't, necessarily make sense, that's okay, and that's actually really, really healthy. And I think that science depends on the general public, like you guys, being able to raise your hands when the scientists are saying things that don't make sense. Now, you might be wrong, you might be completely wrong, but it's okay to ask questions, right? Ask stupid questions, right? And I don't mean stupid because you haven't read about them. I mean, when you read about them and they still don't make sense, ask those questions and ask them loudly, because sometimes they're really important for reorienting our own society. So, and that's kind of the theme that we keep bouncing back to. I already talked about the Oort cloud. I mean, the origin of the solar system and the formation is really that's the biggest topic, I guess, we've been circling around. And in the last 10 years, I've pointed out to you so many different new theories have become accessible in terms of planetary evolution and formation. Even this word evolution that's creeping into planetary science was not there 10 years ago. Just wasn't there. No one would have used that word. And it's really interesting how when we look out to all these other solar systems, we see things happening that are transforming planets from one kind into another, right? We're seeing planets that are very big and cold and Neptune-like, that are getting all of that atmosphere blown away. Some of them are getting blown down to things that look like cores, down to their cores, right? That look a lot like our rocky planets, like Mars and Earth and Venus, right? Because ultimately at the core of each one of those huge icy giants, and potentially at the core of something like Jupiter, is something very rocky and dense that looks a lot like our planet. And so this new way of thinking is just, it's hard to impress upon you how absolutely revolutionary this moment is. It's so revolutionary that it hasn't even made it to the textbook at this point, which is extra revolutionary because the textbook can update in real time. So I wouldn't be at all surprised if it reads differently next year than it does this year in terms of including some of these findings. That I've tried to bring some of those papers in as I found them in the headlines and so forth, but it's really, really something to behold, this kind of paradigm shift. And I don't know that these kind of paradigm shifts come around that often, The theory of evolution was a huge paradigm shift in the Darwin-Wallace days, a few hundred years ago. And I think this one's equally large. But that's the way science works. It's this iterative process of, well, there's a better way to look at things than we used to look at things. And that's what we have to do. And that's what raising your hand and asking questions about things that don't make sense contributes to. And so things move forward, one funeral at a time, right? A lot of people who have spent their lives working on old ideas aren't very apt to give those up. And they can only hold on to them as long as they're around. And then somebody comes along, a new generation comes along, and they have a better idea, and they have no real commitment to the past. So, yeah, how do you explain all of these things? How do you explain the angular momentum problem? How do you explain the fact that Jupiter's got all this angular momentum? Is it a latecomer to the party, right? Did it form separately? We're seeing these big Jupiters out in the Orion Nebula, in these nurseries. We see these pairs of Jupiters orbiting one another with no star whatsoever. So can a Jupiter form by itself, almost like a star, but not quite? And we didn't really talk about how stars form too much, but is it possible that Jupiters and gas giants form without solar systems, and then they find themselves inside of a solar system? Why don't we have a binary partner? Almost all of the other suns have binary partners. Maybe our gas giants formed as were originally, our sun was also similar to that, but it just grew very big, and the Jupiters got left behind, and it took all of their material. I don't know, but the story's not finished, for sure. So, this is really cool. Next semester, we're going to start talking about the sun, and the sun is, one of my friends says it's sort of the Rosetta Stone of astrophysics, right? You guys know what the Rosetta Stone is? It's like how they basically, it was a tablet, I think, that was found by Napoleon, and it had a number of different languages on it, including Egyptian hieroglyphics, and I think Greek, and I actually don't know, I shouldn't say this stuff. Yeah, it basically allowed people to translate the ancient hieroglyphics, right? Because you had all these languages that people actually could read, and you had the hieroglyphics that nobody could read before this. Well, the sun is a magical key because it's so close to us. We have so much data on it. We literally just sent this probe, this Parker Solar Probe, that basically went into the sun's atmosphere, right? We have so much data on the sun. And the better we understand the sun, the more we're going to understand all the other stars. And the sun itself is also at the heart, I think, of some radical paradigm shifts that are going on right now. I mean, this is a huge one that's really, really perplexing. There's all these mysteries about the sun, and as soon as we tap into them, I think we're going to make a lot more progress on the whole cosmos. But we'll talk more about this. I mean, the sun's atmosphere is in the millions of degrees range, right? But its surface is actually quite cool. Now, how does that work, right? There's this is sort of like if you had you put your hand in an oven and the oven was really, really hot, but you touched the walls of the oven and it was really, really cold. It's like kind of boggles the mind in some sense. So what does it mean? Well, it could mean that we don't understand how to translate light into temperature very well. It could mean that there's strange processes going on inside of the atmosphere that we don't understand, different high energy ionization processes. But there's all sorts of interesting questions that it begs that don't make a lot of sense. There's an even bigger revolution about the sun that's underway right now that we'll deal with over the course of a number of classes next semester, which is, I had a friend. I grew up in Ohio, and a lot of my old friends still live there. One of them works in a factory there, and he asked me some interesting questions about the sun at some point. And he was like, "Well, I noticed this thing. We have these like plasma torches, right? And they're working on these plasma torches in the factory, and there's a window that leads into the room where people were doing this work." And the window has like a little bit of an edge on it. You've probably seen these where it sort of acts like a prism and splits the light a little bit. And he noticed that the light that was split from the plasma torches gave these really nice banded structures, right? And we've talked about that. Gases give you these discrete lines when they split the light. But he also saw there was light bulbs in there, and the light bulbs gave this rainbow. He also noticed that the sunlight coming through the window looked more like the light bulbs than like the plasma torches. And he was like, hey man, what's up with that? It's weird. And I was like, yeah, I think you just stumbled on the next revolution in astrophysics, because I think that treating the sun as a big ball of gas is not exactly congruent with the way the sun looks. In fact, the sun has almost the perfect exact spectrum of something that you heated up, like a big piece of molten rock or something like that. And so what's going on? It's a huge, huge mystery to solve. The proposal in order to get that beautiful continuous spectrum involves these million-year relays of photons bouncing around inside of the sun in order to come out at the exact same wavelength to give that beautiful incandescent spectrum that the sun has. Because as you can see, the sun does give you a rainbow. You see it when there's water, right? And then there's, like today, when it's rainy, you can see rainbows if the sun comes out. You don't see those banded structures. So maybe we're on the edge of rethinking about the sun in terms of its actual material composition. There's a very interesting underground argument about that right now, and we'll unpack that with great luxury in the next semester. All right, and then, the last thing that we really touched on in this class, and we'll do more of it too next semester, is the cosmic perspectives and the way that our ancestors have looked at the stars very differently than us. And I hope that I made some impression upon you that these stories that people used to tell about the stars weren't just, I think that you cannot condescend on them as being these silly superstitions. These were the ways that people transmitted their wisdom from one generation to the next, and they used the stars to tell those stories, almost just like I'm using this PowerPoint to tell the stories that I'm telling you, right? And the wisdom that they contained seems to have been really vital to their survival over the years, and it's something that, in some sense, it has become more obscure in our modern age. We don't have a unifying mythology anymore, right? Rationality sort of drove the superstitious elements out of our collective consciousness. I mean, there are still definitely a lot of religious people in the country, but less so than ever before. And so it's not entirely clear that we can get by without a unifying mythology. Every single civilization that's ever existed had a unifying mythology that kind of held its people together. And of course, one of the biggest problems in America right now is that people are far from one nation, right? It's very fragmented feeling. People are in their own little tribes and so forth. And so I think we can learn a lot from the ancient people. You might say that those stories aren't real, and I'm going to read you an example from the Navajo people right now. Actually, sorry, it's from the Lakota people. And so as we think about this, I want you to think about actually how real the story actually can be. I mean, think about it this way. Numbers, right? Numbers aren't real, okay? They're an invention that we came up with, but they work really well. They're an idea. They're just an abstraction, right? You basically take anything and you can quantify it, right? I can count the number of pieces of paper here, and I can perform operations logically on those abstractions, and I can come to conclusions that can allow me to do everything from build a spaceship to, do my taxes, right? So numbers are also an abstraction, just like mythology, but they're very useful. No one would argue that math is pointless or worthless just because it's not real, okay? It's not real in the tangible sense of this table, for instance, right? So I think that you have to start thinking about mythology in a very similar way. It's an abstraction. It does highlight something that's extremely real. And the fact that every single culture comes up with very similar stories without even knowing about one another sometimes points to how real they actually are. So, all right, I want to read you this story. It's a couple pages long, so bear with me. But I think it's really important because it gets at something that I think is missing from our own way of looking at nature that I think needs to come back and maybe will make a comeback in the future, because like I said, it's not clear that people can really survive without an overarching mythology. So this is from the Lakota. There are stories among indigenous people that suggest visitations by extraterrestrial beings, that the stars are their ancestors or carry the spirit of their ancestors, and that when people die, they become the stars or go among the stars. For instance, the Milky Way is described by certain peoples as the land of people who have gone on. There are stories that people come to the earth for a certain period of time and then return to the heavens to become star beings. The following story, Lakota story, is an example. A long time ago, two girls went out one night to watch the stars. One of the girls said she wished she could marry that one big, beautiful star. The other girl said she wished the same about the other beautiful star. Suddenly, they were taken into the star world, and it was there that the two stars became their husbands. Later, the girls became pregnant. They were told that the star world was theirs, but they were warned not to dig any wild turnips. Eventually, one of the girls pulled a turnip from the ground. A hole in the star world opened, and the Lakota woman was able to look down and see the earth and her village. Because she became homesick and wanted to return to the earth, she braided the turnips to make a rope. The braided rope she made did not quite reach, and she fell to her death, although her child had been born. The meadowlark raised her son, since they too speak Lakota. The baby boy was named Fallen Star. Fallen Star reached manhood in days rather than years. He was very tall, and light was always around him. The meadowlark grew old and decided to take him to a Lakota band where he could settle. Fallen Star traveled from band to band. Everywhere he was recognized for being the protector and the bringer of light. A Lakota band was camped near Hamey Park in the Black Hills. Every day a red eagle swooped down and stole a little girl who was carried away to the top of a mountain and killed. All the warriors tried to kill the red eagle but failed. All Lakota people prayed for the help of Fallen Star. He arrived after 7 days, and after 7 girls had been killed. Fallen Star killed the red eagle and placed the spirits of the 7 girls in the sky as a constellation. This constellation is known as the Pleiades in the Western world, and in Lakota, I'm going to mess this up, Winsinakala Sakowin, which means the 7 little girls. Another constellation is called Nape, which means hand in Lakota. To locate this constellation, one must first find Orion. The Orion belt comprises the wrist, Regal, the pointer finger, and Eratinus Beta, the pinky. A story related to the constellation begins long ago when Fallen Star told everyone that he planned to marry the daughter of a chief in a nearby village. She told Fallen Star that the thunder beings had taken away her father's arm. She agreed to marry Fallen Star if he could get the chief's arm back. Fallen Star went in search of the arm, and he obtained special powers as he traveled through different villages. Fallen Star obtained sinew, a wren feather, a swallow feather, a live coal, an eagle plume, and many words of power. All of these things helped Fallen Star change his shape and escape the thunder beings. As Fallen Star traveled, he was in the Black Hills, but at the same time he was traveling through the star world. He visited 3 villages of star peoples, and it is said that his son would have to visit the other 4. Finally, Fallen Star reached the thunder beings. By changing into a wren and then into a man, he was able to outwit the thunder beings and the trickster. Fallen Star recovered the chief's arm, and using the other powers he was given, he was able to flee. Fallen Star gave the arm to the chief, married his daughter, and later they had a son. The purpose of this story is to provide teachings. The chief represents selfishness for wanting his arm back. The thunder beings represent the annual disappearance of fertility as well as the masculine power to refertilize. The arm symbolizes the earth. The power of life is lost and regained each year, but not without sacrifice. People who argue that such stories are wholly unscientific are begging the question of probabilities and possibilities. We know that life on Earth likely resulted from supernova activity, that is, a combination of certain electromagnetic radiation and bombardment by particles of matter. Thus, the notion that we are star people or stardust is actually quite reasonable. Currently, Western science says that yes, all life on Earth is stardust, or comprised of the same elements as stars. Some of the necessary elements that made life possible on Earth could not have come from anywhere else but bombardment by asteroids. And of course, if it happened in this solar system, it most certainly happened in other solar systems. So, that's just one interpretation of that story, and I think that there's probably many, 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 many interpretations possible. And that's what's incredible about myths, is that it seems like the more that you look at them, the more meaning you can actually uncover. And I think that people have a much easier time talking about other people than they do about themselves. And so what I think that people have done traditionally is they've used these sort of supernatural beings to generalize their own experiences and put them on the stage and be able to dissect them accordingly without actually endangering their own experiences. Oops, I lost my pencil. So this moves us towards thinking about our own cosmology, right? Because cosmology really just means who we are as people in relation to the whole universe. And cosmology wasn't a science until about 50 years ago. And traditionally, cosmology has, across thousands of years, philosophers have asked basic questions like, what's the origin of the universe? What was the cause of there being a universe? Is it necessary that existence even occurs, right? Is it necessary for us to be here? Or could it have gone a different way? Physical cosmology, the one that's actually become a science, is actually asking very much the same questions. And the reason that they're even able to put that inside of the science department is based only on really a couple of lines of evidence. One of them is this thing they call the cosmic microwave background radiation, which we'll talk about. Another one has to do with the way that the distant stars and galaxies appear to be receding away from us, which, by deduction sort of points to the idea that there was an origin point. And then there's some other arguments regarding the different isotopic abundances, so, the spread of atoms in the universe. But it's actually a very, very narrowly defended scientific enterprise, and it's on the ropes a little bit right now because these new telescopes are finding really interesting contradictions to this story. And I think what's most interesting about this modern scientific cosmology is that it's really not that different than the cosmology that almost all of these ancient peoples were telling, right? Basically, we've told a story in modern science about the birth and the death of everything, which is very much reflective of our own lives, because you probably noticed that the most difficult thing to deal with in life is the fact that, well, you're going to die, first of all, and so is everyone that you love and everything you've ever known. And this is, in some sense, the fundamental crisis of being a human that I think other animals don't have to deal with so much, is that you're very well aware that you're sort of on this ticking time bomb of a ride that's going to run out at some point. And so it's not surprising to me that people have told that same story about the whole universe itself. The universe was born, the universe will die, there's work to be done in the meantime, something like that. And in some sense, over the past 100 years, there's been a scientific argument to substantiate that worldview. But I don't think that it's really possible for people to separate out their own beliefs that they inherited from the ancestors about that, from the way that they look at the data when they analyze the sky. And so next semester, we're going to ask some really huge questions like, what's the alternative? If this Big Bang theory falls apart, what are we left with in its aftermath? Is eternity even conceivable? What does that mean? Do we need to have an origin for the universe? Or is that just something that we're putting upon it because that's the way our own lives go? And what would that change about all of these stories that we've been telling even in planetary science if we had that kind of a time span to make things happen? All right, so one thing is absolutely certain is that the more information we get, the more complexity we see. This is a reconstruction of galaxies each one of these little blobs is actually a whole galaxy. And this is just in our local neighborhood. But what we see is that the galaxies are organized into structures that are very, almost like a web, right? Or they almost look like neurons in a brain or something like that. There's big scale structures that we couldn't have ever even imagined were the case. It actually seems like rather than the universe having blown up and gotten increasingly, they used to call it like the heat death of the universe, right? Where the universe just flies apart and everything kind of goes from this very ordered state in the beginning to this very chaotic state. actually seems to be like we're discovering very much the opposite. There's big scale structures that we're noticing that are being organized on the cosmic scales, right? And what does that mean? What's going on? What sort of interactions are happening at this level? Is there life possible at larger scales? That's a really interesting question, you know? And then, you know, as far as, if you think there's a lot of mysteries in planetary science, just wait till we get to cosmology and astrophysics, because, you know, in order to make some of these models work, we have to populate the universe with mostly stuff that we can't see. We call it dark matter or dark energy, and it's basically a placeholder in our equations, because gravity stops making sense in terms of organizing structures like this, in terms of organizing how the galaxies turn as a whole. It doesn't make sense using just the masses of the stars, so something else is going on. And the temporary solution that people have come up with is they stick a variable in there to make up for all of that mass, which they call dark something, you know, dark matter, dark energy. And it makes up the overwhelming majority of the stuff in order to make this model work in terms of gravity alone. So we're going to explore that in great depth next semester and really explore how to look at these dark things as actual mysteries as opposed to supernatural solutions to the problems, which is really not what we're after in science. We want to come up with natural, mechanistic understandings of how these things work. And so these are incredible open pages. So I guess just to put a bow on all of this, I hope that all of you guys will go out and participate in science and be curious and raise your hand when you have questions and talk to your friends about it. And don't just assume that, you know, the certainty that you read about in the headlines means that these puzzles are solved. And if you hear things that sound superstitious in science, it probably means that's just a place that's needing to be developed, right? You know, some of these really, really common terms that we hear nowadays, like the forces, right? The force of gravity. Like, this is one of the most superstitious things I've ever heard of in my life, right? It sounds like Star Wars, right? Right? The force, right? What is a force? And how does a force do anything, right? Well, it's clearly that we don't understand. We don't understand how gravity works is what it comes down to, right? We don't understand how gravity works at large scales, especially. We don't understand how galaxies stick together, so we insert dark matter into them. We don't understand how certain bodies can orbit points where there doesn't seem to be anything at all. And so we invent these things called black holes to deal with them, right? There's all of these interesting points that, you know, if they sound superstitious and they sound like they don't make sense, that's probably something you should follow your intuition on, because that's where the real progress is going to be made. And honestly, our ability to rethink these problems is the only thing that has gotten us this far and gotten us to the place where we have a heated building with lights on overhead. We've been able to stop at each point and rethink all of the things that we had absolutely believed were the case. And sometimes people have lost their lives defending those ideas, right? Let's not forget Bruno and Galileo. Galileo didn't die, but house arrest, right? So it's not easy to change the weights when all of society has gotten behind an idea that they think is absolutely brilliant. It's very, very difficult. It actually can be a fatal thing to do in some cases. And so we have to be brave, and we have to be willing to ask those stupid questions. We have to, you know, Galileo's question, Copernicus's question were pretty stupid questions in their day. What do you mean? What do you mean that the sun shouldn't be revolving around the Earth? That's a stupid question. But it turns out it was a brilliant question. Same with Darwin. What do you mean the species didn't always look like this? That humans haven't always looked like this since the beginning? Stupid question, but actually quite brilliant. And you know, those might seem like sort of remote ideas, but if you think about the technological progress, the fact that we're using those Galilean ideas, those Copernican ideas, led to Newton's ideas about gravity, which led to our ability to explore space and do these rocket missions and all of this, right? Darwin's ideas about evolutions have led to the development of a lot of modern medicine. We literally evolve different molecules in petri dishes right now in order to make medicines, right? So changing our minds is absolutely critical to the enterprise of science, and there's always going to be I'm going to use the word force. There's always a force in society that wants to keep things the same. There's always people who want to hang on to bad ideas because, well, they've worked for so long. Why should we move on? But it's our job, just as the general public, to raise our hands and say, hey, this doesn't make sense. This doesn't make sense. And keep asking it until we move through it. Anyways, it's been a pleasure having you guys in class, and I really look forward to seeing, I hope to see some of you guys next semester. And good luck with the rest of your finals. Have a wonderful holiday season, and let's call it a day.